found out the response of this single degree of freedom system to a direct delta function or unit impulse, and we have also found out its response to a step function which is u of t minus tau. So a quick recall, how does a function u of t minus tau look like? So if I plot its graph, this function becomes 1 on just right hand side of the event when t minus tau becomes 0. So for any value of t minus tau greater than 0, this function assumes the value of 1. This is the correlation. So for any value of t minus tau greater than 1, the function has the value of 1. Whereas for any value less than or equal to t minus tau equal to 0 or less than or equal to 0, the function has 0 value. This is how u of t minus tau look like. So this we have already discussed in previous class. So if t minus tau has to be equal to 0, that means t has to be equal to tau. So at t equal to tau, this function will change to 1 from 0. So about t equal to tau, on left hand side it is 0, on right hand side on left hand side and at tau it is 0, but just right hand side of tau it assumes the value equal to 1. This is how the function u of t minus tau, or in other words, Heaviside step function looks like. Are you with me? Please type your response in chat box if you remember this discussion. I'm waiting for the response. Yeah. So Shreyas says yes. So let us go ahead. Now we have already found out the response of single degree of freedom system to such kind of excitation by solving a second order homogeneous differential equation. उसको हमने solve किया था. If you remember, it becomes non-homogeneous equation. The equation looks something like this: mx double dot mu double dot of t, mu double dot of t plus cu dot of t plus ku of t is equal to f of t. This is how the equation looks like. And f of t in this case is u minus tau. U of t minus tau, I'm sorry. And we have already found out that the response of this system is 0 till t equal to tau, because no load ordinate is present till time t equal to tau. And after t equal to tau, we have evaluated its response by solving this second order differential equation for appropriate initial conditions. I hope everything is in place. Now we are going to solve the same problem. We are seeking the response of this single degree of freedom system at arbitrarily chosen time t. तो ये small t यहाँ पे मैंने दिखाया है, देखो. So from here till here, the duration of time is t. T is arbitrarily chosen. T can be varied from 0 to infinity. So we seek the response of this single degree of freedom system from t equal to tau to t equal to infinity. कहां से कहां तक? t equal to tau to t equal to infinity. Why not t less than tau? Because when t is less than tau, the response is going to be 0. We know that the load has not appeared on the system. So therefore, during time t equal to 0 to t equal to tau, the response of the system is not going to be there. So we are interested in seeking the response of a system from time t equal to tau to t equal to infinity. Are you with me? So this is our problem statement. We have already solved this using one of the methods by solving differential equation, but now we are going to do this task by knowing the impulse response vector. Impulse response of a SDOF system, single degree of freedom system. So we already know the response of this SDOF system to impulse at time t. Are you with me? So for that, let me share the screen of previous lectures with you. 1 minute. That was covered, if I am not wrong, it was covered in lecture 8. Yes. सो जरा यहाँ पे ध्यान से देखो, जस्ट अ सेकेंड. Yes. So that's what we have. So that's what we have done. See, we have a unit impulse acting here. So f of t, if it is a unit impulse at time tau, then what is the response of the system? That response we have found out. And what can you tell me what is the response? So the response looks like e raised to minus neta omega t minus tau 1 upon m omega d sin omega d t minus tau. Are you with me? Vedant, can you unmute yourself?
Yes, sir. Yes, sir.
Yeah. So now जरा यहाँ पे ध्यान दो, this tau and the tau here is going to have conflict of notations. So here, instead of saying it at tau, I will say that the impulse is acting at time, let us say capital T. Are you with me?
Yes, sir.
So let me come back here. So what is the response of this single degree of freedom system to a unit impulse at time t? Let me try to answer that question. So let us say if f of t would have been delta t minus capital T. So what is capital T? Capital T is the time at which that unit impulse is applied. Are you with me?
Yes, sir.
अगर ये सिर्फ इतना यूनिट इम्पल्स इस सिस्टम के ऊपर एक्ट होते रहता, तो उसका ये फंक्शन कैसे दिखने वाला है, आप जरा बताओ मुझे. हाउ डज दिस फंक्शन लुक लाइक? दिस इज टाइम. So at time t equal to capital T, you are going to have a impulse where the magnitude reaches infinity. Are you with me?
Yes, sir.
This is how the direct delta function at t minus direct delta function of t minus capital T looks like. Happy?
Yes, sir.
And what is the response of the system to this impulse? Single degree of freedom system का response क्या है? So I am going to write down u of, क्या लिखूं यहाँ पे? I should write u of t minus t. Are you with me?
Yes, sir.
जैसे यहाँ पे लिखा था, देखो u of t minus tau लिखा था ना.
Yes, sir.
But at tau I am now going to call it as t. So u of t minus capital T is equal to, क्या लिखो, e raised to minus eta omega t minus t. Happy? Then 1 upon m omega d happy, into sine of omega d t minus tau. So sine of omega d t minus capital T. Are you with me?
Yes, sir.
This is the response of this single degree of freedom system for an unit impulse that occurs at time t, capital T. Happy?
Yes.
Question. In the actual force diagram, at time t, if I consider a small increment in time dt, the area under this force versus time curve, can I idealize it as a small impulse? देखो,
Yes, sir.
ये impulse होगा कि नहीं? And how much
Yes,
is
sir.
that impulse? Can you tell me the magnitude of that impulse? It is going to be 1
1 into dt.
into dt. So if this is response of the system to unit impulse is this one, what will be the response of the system at the same time capital T, but of magnitude dt? Are you getting my question?
Yes, sir.
What will be the response of this single degree of freedom system to an impulse of magnitude dt at time t? I know the response of single degree of freedom system to unit impulse at time t. Do you agree with me?
Yes, sir.
यूनिट इंपल्स का पता है तो dt का कैसे पता चलेगा? उसको dt से मल्टीप्लाई करना पड़ेगा. Do you agree with me?
Right. Yes, sir.
So now look at what I am trying to write down. I am going to write this as du. What is du? It is the x directional deformation produced at time t minus capital T. Are you with me?
Yes, sir.
By which impulse?
dt. For time dt.
Just a minute. U of t minus t, which it will be equal to e raised to minus eta omega t minus capital T. Are you with me? Into bracket
Yes,
1 upon m omega d sine of omega d t minus capital T. ये exactly into dt. ये exactly क्या है जरा बता सकते हो? This is the response of the impulse dt which occurs at time capital T, and the response is calculated at time small t. Are you with me?
Can you please repeat this sentence?
Yes, I will repeat the sentence. We will take the numbers so that we don't get jumbled up, things jumbled up. So let us say this t is 7 seconds. Happy?
Yes, sir.
Let us say this t, for sake of argument, is 30 seconds. Are you with me? Are you with me?
Yes, sir.
Now, at time t equal to 7 seconds, what is the impulse that this single degree of freedom system is subjected to? dt multiplied by 1, which is nothing but dt. Do you agree with me?
Yes, sir.
What is its response at time t equal to 30 seconds? उसके लिए हमारे पास expression है. Do you agree with me?
Yes, yes.
So ये जो impulse दिख रहा है ना आपको dt magnitude का, उसका response at time t equal to 30 seconds क्या रहने वाला है? ये 30 रहेगा, ये 7
Minus
रहेगा.
7.
Are you
Yes.
with me? So e raised to minus eta omega 23 1 upon m omega d sin omega d 23 dt. Do you agree with me?
Yes.
This is the response of this small impulse dt at time t equal to 30 seconds. समझ में आ रहा
Yes.
है? अब मैं फिर से वो मेरा जो सेंटेंस था उसको रिफ्रेश करता हूं, मैं रीइटरेट करता हूं. So therefore what we have written is the response of single degree of freedom system at time small t. Do you agree with me?
Yes, sir.
Due to impulse dt applied at time capital T. समझ में आ रहा है?
Yes, sir.
फिर से एक बार. Whatever we have written down below is the response of single degree of freedom system at time t equal to 30 seconds due to a impulse of magnitude dt applied at time t equal to 7 seconds. Happy?
Yes, sir.
फिर से. So whatever we have written down below is the response of the single degree of freedom system to impulse dt applied
Yes.
on the system at time t equal to 7 seconds and the
Yes.
response being monitored at time t equal to 30 seconds. Happy?
Yes, sir. Yes, sir.
अब जरा यहाँ पे ध्यान दो. I don't want the response of this system to this single impulse. I want the response of the system, single degree of freedom system at time t equal to 30 seconds due to all the impulses that are encompassed before time t equal to 30 seconds. Do you agree with me?
Yes, sir.
Now, whatever is the lower contribution before time t equal to 30 seconds, can I split it into a large number of train of impulses of magnitude dt? Do you agree with me?
Yes. Yes.
जैसे हम पॉइंट लोड को करते हैं ना, वही कंसेप्ट आया. आप क्या करने वाला? आई एम एज्यूमिंग दैट द सिस्टम इज रन, सिस्टम has been applied a train of impulses starting from time t equal to tau, right, to
Yes, sir.
t equal to 30 seconds. मतलब t equal to t. Are you with me?
Yes, sir.
सो टाइम t इक्वल टू टाउ से लेके टाइम t इक्वल टू t तक इसमें बहुत सारे ऐसे छोटे छोटे impulses आए at different values of capital T. Do you agree with me?
Yes, sir. Yes, sir.
So now how do I write down the response of all those impulses at time t equal to 30 seconds? तो क्या करना पड़ेगा? I will have to now, by the way, there is a small correction in notation. If I'm calling this as t, this has to be d capital T, not small t. Are you with me?
Yes, sir.
dt है ना? तो यहां भी किससे मल्टीप्लाई करना पड़ेगा? d कैपिटल T से, नॉट स्मॉल t. हैप्पी?
Yes, sir.
So now if I want to find out the response of the system at time t, मुझे क्या करना पड़ेगा? इसको इंटीग्रेट करना पड़ेगा from t equal to tau to t equal to small t. Do you agree with me?
Yes, sir.
Therefore I have multiplied it. T tau to t is the limit. Happy?
Yes, sir.
And what is the variable of integration? Variable of integration, mind you, is capital T, not small t. Are you with me?
Okay, sir.
Chalo. I am very sure that many of you are going to have many doubts in this. So therefore I have decided that I am going to re-explain all these things. एक बार फिर से explain करने वाला. I don't want any stone unturned. हाँ, therefore फिर से explain करता हूँ. Are you with me?
Yes, sir.
चलो, फिर से एक बार मैं ये ग्राफ यहाँ पे प्लॉट करता हूँ. u of t कैसे दिखता है? f of t कैसे दिख रहा है? जरा बताओ मुझे. f of t looks something like this. At time tau, it shifts from 0 to 1. Do you agree with me?
Yes, sir.
So यहाँ पे ये वैल्यू कितना है? 1 है. इसके पहले ये वैल्यू कितना है? 0 है. Now what I am going to do is I am interested in finding out the response of this single degree of freedom system when subjected to this f of t, but I am interested in finding out the response at time t, which is arbitrarily chosen. T can vary. Are you with me?
Yes, sir.
This t can vary from tau to infinity. Happy?
Yes.
At that time, I am interested in finding out what is the value of u of t. Do you agree? Do you agree with me?
Yes.
U of t is what? For all the values of t greater than tau, because जो less than tau के values है t के, वहां तो response 0 रहने वाला है. Are you with me?
Yes, sir.
So this is what I am interested in. अब उसके लिए मैंने क्या किया? उसके लिए I have divided now this entire signal up to time t equal, entire load signal up to time t into small strips. देखो, 1 2 3 4 ऐसे n strips में मैंने डिवाइड किया. Are you with me?
Yes, sir.
Each of this strip, चलो देखो, इसका width कितना है टाइम में? It is d capital T. And at what time does this strip start? It starts at time capital T. Are you with me?
Yes, sir.
So you will understand that this capital T is going to change from tau till small t. Do you agree with me?
Yes, sir.
हाँ, तो ये t कहां से कहां तक चेंज होने वाला है? टाउ से लेके कैपिटल t तक. When I go on changing t, I get a new impulse. Do you agree with me?
Yes, sir.
हाँ, तो जैसे जैसे मैं t चेंज करते जाता हूँ वैसे नया नया इंपल्स मिल जाता है. नाउ माइंड यू, दिस फर्स्ट इंपल्स, जो ये पहले वाला इंपल्स है, जिसको मैं अब डबल हैचिंग से दिखाऊंगा सो दैट देयर इज नो कंफ्यूजन. This impulse is going to have some u of t at time t. Do you agree with me?
Yes, sir.
Similarly, the second impulse is going to have some u of t at time t. Do you agree?
Yes, sir.
Third impulse, fourth impulse, fifth impulse, nth impulse is going to have some effect on u of t at time t. Do you agree with me?
Yes, sir.
If I add the response generated u of t by each of these impulses together up to time t, then I am going to get the response of the system at time t. Do you agree with me?
Yes, sir.
This operation precisely in the limit as dt tends to 0, we do it by integration. Do you agree with me?
Yes, sir.
So सबसे पहली चीज मैंने क्या की, I found out the response of this system at time t, small t, due to impulse that is that is applied at time capital T. And what is the magnitude of impulse? 1 into dt. Do you agree with me?
Yes, sir.
So what is the response of this impulse at time small t? That we already know. That response is u of t. That response is in e raised to minus eta omega t minus capital T into bracket 1 upon m omega d sin omega d t minus t into dt. Why did I multiply by dt? Because this much is the response for unit impulse. Are you with me?
Yes, sir.
लेकिन हमारे हाथ में कौन सा इंपल्स है? वी हैव द इंपल्स ऑफ मैग्नीट्यूड dt. यूनिट इंपल्स के लिए इतना, तो dt मैग्नीट्यूड के इंपल्स के लिए कितना? dt मल्टीप्लाइड बाय दैट रिस्पांस. डू यू एग्री विथ मी?
Yes.
So whatever I am writing here is the response of the single degree of freedom system at time small t due to a impulse of magnitude d capital T at time t. Do you agree with me?
Yes.
So what is the response of this entire load? Entire load का response क्या रहेगा? I will have to integrate it from t equal to 0 to t equal to small t. Do you agree with me?
Yes, sir.
So that's what I have written. Now hopefully everyone is clear about this expression now. Are you with me? Vedang, is it clear?
Yes, sir.
Now imagine instead of this function, there can be any arbitrary function. It's all right. I am going to do the same thing. It is the train of impulses with varying magnitudes. Happy?
Yes, sir.
So that's what we will see, that how to do that a little later. But let us first complete this. Now till this point, is everybody on the same page? Please type your response in chat box. I am waiting for the response. Then I will go ahead. Vedang has already said yes. Vaibhav says yes. Rajarshi says yes. Malay says yes. Anyone? Shreyas, yes. Okay. Okay. Amrut says yes. Okay. So we will go ahead with this now. अब जरा यहाँ पे ध्यान दो. Just a second. We will take a digress now because I want to convey one more point to you. Digress. जरा मुझे बताओ आप ये इंटीग्रेशन क्या रहता है? I am doing integration 3x dx where the lower limit is 3 and upper limit is x. Yeah, tell me what will be the integration? Vaibhav? No, not Vaibhav. Vedang.
So 3x square by 2.
3x
Limit.
square by 2 is the integration, and we have to put the limits, right?
Yes.
So what will be the integration?
3x
3x
square
square by 2
2 minus
minus
3 into 9 by 2.
so 27 by
2.
27 by 2. Do you agree with me?
Yes, sir.
तो अब जरा देखो, when what was the variable of integration here? Can you tell me what was the variable of integration?
X.
Yes, when x is the variable of integration and the limits, one of the limits are functions of x, the result is also a function of x. Do you agree with me?
Yes, yes.
Happy?
Yes.
अब जरा यहाँ पे देखो, अब दूसरी चीज करते हैं. Let us continue this digress. 1 minute. Let me do an integration 3 to y of 3x dx. बोलो क्या होगा? 3x
3
square by 2,
2
right? and the limits are 3 to y. So it is going to be
Yes.
what? 3y square by 2
2.
minus 27 by 2. Do you agree with me?
Yes, sir.
Now tell me, uh, what is the variable of integration?
X.
X. Variable of integration, is it visible in the result?
No.
No. But the limit is a function of, one of the limits is a function of y. So therefore this
Yes.
integration is a function of y. Do you agree with me?
Yes.
Now let us extend this here. Tau is a constant. Tau is constant. This is like number 3 here. Are you with me?
Yes. Yes.
What is the variable of integration here? Variable of integration is capital T. Mind you,
Capital
integration
T.
is occurring over capital T. So small t will be treated as a constant. Are you
Yes.
with me? So variable of integration here is capital T. And the limit is a function of small t. So what do
Yes.
you think? This u of t will be function of what? Will it be function of capital T
Small
or
t.
small t?
Small
Small t.
t.
I just demonstrated that. अगर मैंने ऐसे ही स्टेटमेंट बोल दिया होता तो थोड़ा सा हेवी हो सकता था, इसलिए मैंने डेमोन्स्ट्रेट किया. Are you with me? So we understand now that u of t is a function of t. Do you agree with me?
Yes, sir.
हाँ. अब जरा यहाँ पे देखो ये इंटीग्रेशन कैसे आया. व्हाट काइंड ऑफ इंटीग्रेशन दिस इज. It is a function, means very complicated integration, because you have a complicated function sitting here and complicated function sitting here. Are you with me?
Yes, sir.
So it is not always possible to analytically evaluate this integration, and therefore you may have to use numerical methods to evaluate this integration. Are you with me?
Yes, sir.
So whenever you are equipped with the capability of programming for numerical methods, we will use this strategy to predict the response of single degree of freedom system to any arbitrary loading. Are you with me?
Yes, sir.
But when you use numerical methods, you will what you are going to essentially do is, let us say you want the response from time 0 to 30 seconds. So you will divide the interval into 100 points. So 0.03 seconds, 0.06 seconds up to 30 seconds. ऐसे करोगे आप 1000 points. Are you with me?
Yes, sir.
And at each point you are going to solve this integration numerically, and then you are going to write down that value. How we are going to do that, I will show you in MATLAB programming in this course. So in this course we are also going to do programming in MATLAB, maybe as a lab exercise, but let us see. So there I will show you how to handle this solution numerically. Are you with me?
Yes, sir.
If you want the analytical solution, I have shown the earlier method where you have already got the solution as a function of known parameters. It does not involve any integration and all. Are you with me?
Yes, sir.
Okay. So that's the idea. That's how we use impulse response of single degree of freedom system to predict the response of the system to any kind of general load. Are you with me?
Yes, sir.
Now, we will proceed ahead, and I'm going to now take another form of load. That numerical solution we will do probably during the lab class, but the theoretical part I have covered here. Are you with me?
Yes, sir.
Yes. Now we are going to deal with another type of loading. So let me borrow the sketch of single degree of freedom system here. Gradually, we are going towards the complicated loads. Are you able to understand that?
Yes, sir.
Okay. This is the single degree of freedom system. And now let us say it is subjected to f of t, which looks something like this. I'm going to draw now the variation of f of t. Are you with me?
Yes, sir.
Let me call this as t1 and let me call this as t2. F is the magnitude. Are you with me? So this system is subjected to a sudden increase in force F, sudden increase in the force magnitude by amount F at time t equal to t1, and then the force suddenly drops. So suddenly applied load and then suddenly released load. Are you with me?
Yes, sir.
Now, how does system respond to this? Tell me. You have to use all the tricks in trade and write down the response of the system to this excitation. कैसे लिखोगे बोलो? What am I interested in? देखो 0 to t1 तक तो सिस्टम का रिस्पांस 0 रहने वाला है. Do you agree with me?
Yes.
So this is u of t. Of course, this has a mass m. U of t is going to be 0 for t between
Between
0 to
0 to
t.
T1.
Very good. तब u of t 0 रहने वाला. So question कब आएगा? I will be interested in finding out the response of the system for t greater than t1. Do you agree with me?
So between T1 and T2.
No, not necessarily. I'm also interested in finding out the response of the system at times slightly larger than t2. Are you with me?
Okay. Okay.
So I'm interested in finding out response of the system u of t at time t greater than t1. Happy?
Yes.
सो t ग्रेटर देन t1 ये जो इंटरवल है उसके हम दो पार्ट करेंगे. क्यों करेंगे? वी विल सी इट. बट देयर आर टू पार्ट्स. वन, t between t1 to t2. Are you with me?
Yes, sir.
And t from t2 to infinity. What can you say about the response of the system from time t2 to infinity? Bolo.
So 0.
No, it won't be 0. I was afraid that you will say that. Dekho, here the system was not initialized at all. It was at rest. Nothing happens to the system from time 0 to t1. And therefore, the response of the system is 0. Are you with me?
Yes, sir.
But here, there is a sudden drop in load here. There is a sudden application at t1 and sudden drop at t2. So, corresponding to sudden drop in load t2, the system is going to exhibit the vibrations. Are you with me?
Yes, sir.
And those vibrations will be experienced beyond T2. So therefore, the system response is not 0 after time T2. It will tend to 0 for very large value of time. Are you with me?
Yes, sir.
Whereas the system was at rest and it was not initialized, it was not disturbed before time T1. From time T equal to 0 to T1, the system was at rest. It had no previous load history. Are you with me?
Yes, sir.
Therefore, at that time, the response is 0. Are you able to understand what I'm trying to say?
Yes, sir.
Okay. So now these are the two intervals in which we are going to divide the response of the system. And why do we do so? There is a purpose. Because if I ask you what is the response of the system u of t in time t which is greater than t1, which is greater than t1 but less than t2, less than equal to t2. Are you with me?
Yes, sir.
So your t lies somewhere here. So isn't it very similar to the earlier case? देखो इसके
Yes,
जैसा
sir.
ही है कि नहीं? You want to find out the response at time t. Are you with me?
Yes, sir.
Which is between t1 and t2. So if I draw a line at t, it is going to intersect this step curve, and on either side the load has not dropped down to 0. Are you with me?
Yes, sir.
So here in this phase, I can straight away write down the response same as the earlier one. Do you agree with me?
Yes, sir.
So do we have the expression for that? Yes, in the last class we had derived the expression. Do you agree with me? Let me open that.
Yes.
This is the expression. Happy?
Yes, sir.
U of t star is equal to U of t minus tau. तो यहाँ पे क्या होगा जरा बताओ. Tau उसमें tau is now replaced by t1. Do you agree with me?
Yes, sir.
तो यहाँ पे जो tau दिख रहा है वो that I am going to replace by t1. Happy?
Yes, sir.
So वो रिस्पॉन्स क्या है? e raised to minus eta omega. यहाँ पे t minus tau था, यहाँ पे क्या होगा? t minus t1.
P1.
Happy? And t
Yes.
is between t1 and t2. T has not crossed t2. Are you with me?
Yes.
हाँ, तो अब जरा देखो नेक्स्ट. व्हाट इज नेक्स्ट? in bracket minus f by k. Do you agree with me?
Yes.
Minus f by k cos of omega d t minus
T1.
yes, very good. Then minus f eta omega upon k omega d
Omega D. Sin omega D.
sin omega d
T minus T1.
t minus t1. Happy?
Plus F by K.
Plus f by k. So I'm going to write that plus f by k. This is the response of the system. Do you agree with me?
Yes, sir.
This is in which time? When
Between-
t is between t1 and t2. This is important.
Yes.
Happy?
Yes.
Now what happens after time t2? If I seek the response for any t greater than t2, अब क्या होगा जरा बताओ मुझे. अगर मैंने यही रिस्पांस लिख दिया, यही वाला, तो वो किसका रिस्पांस होगा? इट विल बी रिस्पांस टू ए एक्साइटेशन वेयर f कंटिन्यूज अप टू t. डू यू एग्री विद मी?
Yes, sir.
हाँ, मतलब हम किसका रिस्पांस लिख रहे हैं जरा देखो. अगर यही रिस्पांस मैंने रिपीट किया, आई विल फॉर द सेक ऑफ आर्ग्यूमेंट आई एम गोइंग टू ड्रॉ दिस f of t once again. थोड़ा सा पेशेंस और अंडरस्टैंडिंग लगेगा. इट्स नॉट वेरी डिफिकल्ट. दिस इज t1. Are you with me?
Yes, sir.
This is t2. And अगर मैंने यही रिस्पांस यहां भी लिख दिया फॉर ए टाइम t विच इज ग्रेटर देन t2, तो वो कौन से लोड के लिए होगा? किस तरीके के लोड के लिए होगा वो रिस्पांस? वो लोड में रेड कलर लिखाऊंगा. That will be the response of a system to this kind of load. Do you agree with me?
Yes, sir.
ये पूरा होगा लोड. Are you with me?
Yes, sir.
लेकिन T2 के बाद ये लोड तो है नहीं. Do you agree with me?
Yes, sir.
That means I will have, from the response of SDOF system to this kind of load, I will have to subtract the response of the same SDOF system to this load. जरा देखो यहाँ पे कैसे ड्रॉ कर रहा हूं. देखो ओरिजिनल लोड अगर मुझे रिकवर करना है तो कैसे रिकवर करना पड़ेगा? देखो, सब्ट्रैक्शन ऑफ दिस टू डायग्राम्स विल गिव मी द ओरिजिनल लोडिंग डायग्राम. डू यू एग्री विथ मी?
Yes, sir.
Oh no, sorry, I have made a mistake. The response was, if I write down the same response as above, it will be for the loading of this nature. From T1 onwards, the load is constant. Do you agree with me?
Yes, from T1 onwards.
हाँ. So यही response अगर मैं यहाँ भी लिख दूं for T greater than T2, it will be response for this load. Do you agree with me?
Yes.
उसमें से अगर मैंने response for this much load subtract किया, then I am going to original loading diagram. Do you agree with me?
Yes, right. If we subtract that.
If I subtract that, तो अब जरा देखो what I am seeking the response of the same single degree of freedom system but with tau equal to t2. Do you agree with
Yes.
me? हाँ, तो मतलब अब सब्ट्रैक्शन करना है रिस्पॉन्सेस का. कौन से रिस्पॉन्सेस का सब्ट्रैक्शन करना है? द रिस्पॉन्स ऑफ सिंगल डिग्री ऑफ फ्रीडम सिस्टम टू this kind of load and response of single degree of freedom system to this kind of load. Happy?
Yes.
तो वो कैसे लिखूं? So I am going to borrow this expression here. ये एक्सप्रेशन मैंने बोरो किया एज इज. देखो, लेकिन now the response of the system will not be merely this much. Happy? अच्छा बोलो, यहां तक का रिस्पॉन्स के लिए है, बताओ.
This was for time T1 to T2.
हाँ, this was for this loading. Do you agree with me? इस लोडिंग का रिस्पॉन्स ये है. डू यू एग्री विथ मी?
So between T1 to T2 it was, but the diagram is more than T2.
No, I am considering the second case now.
Okay, sir.
Are you
Okay,
with
okay.
me? So if time t which is greater than t2, if I write the same response, it will be response to not the original loading. It will be this kind of loading which continues up to t. That's what I'm saying. Is it right?
Yes, sir.
Are you able to understand my point?
Yes, sir.
लेकिन ओरिजिनल फोर्स डायग्राम कैसा है जरा बताओ मुझे. इन ओरिजिनल फोर्स डायग्राम वी डोंट हैव द इंटेंसिटी फ्रॉम t1 टू t2, फ्रॉम t2 टू t. डू यू एग्री विथ मी?
Yes, sir.
तो क्या करना पड़ेगा? जो या इस लोडिंग में मैंने एडिशनल लोड दिया है t2 टू t, वो सबट्रैक्ट करना पड़ेगा टू गेट द ओरिजिनल लोड. डू यू एग्री विथ मी?
Yes, sir.
So if I subtract this diagram from this diagram, I recover the original load. Do you agree with me?
Yes, sir.
Original f of t, for which I am seeking the response of single degree of freedom system. Do you agree with me? This one.
Yes.
I will copy this down. देखो, are you with me?
Yes, sir.
So this minus this gives me this force versus time behavior. Do you agree with me?
Yes, sir.
If I know the response of single degree of freedom system to this loading and response of single degree freedom system to this loading, if I take the subtraction of responses, it will be the response to this function. Do you agree with me?
Yes, sir.
That's what I am going to do. So already I know the response of the system for this loading. वो कैसे लिखा है? यहाँ पे लिखा है. Are you with me?
Yes, sir.
इसमें से मुझे सब्ट्रैक्ट करना पड़ेगा. कौन सा रिस्पॉन्स सब्ट्रैक्ट करना पड़ेगा? Response of the single degree of freedom system to this kind of loading. Do you agree with me?
Yes, sir.
वो क्या है रिस्पॉन्स, बताओ जरा. इसमें टाउ के जगह सिर्फ t2 दिखाना है. Are you with me? It is as if the load started from t2 and then it is constant. Happy?
Yes. Yes.
हाँ, सो वही करने वाला हूँ. ये सिस्टम का रिस्पॉन्स मैंने ऐसे के ऐसे रख दिया. दिस इज उसमें से अब सब्ट्रैक्ट करना है. क्या सब्ट्रैक्ट करना है? द सेम थिंग, बट आई विल हैव टू रिप्लेस t1 by t2. Do you agree with me?
Yes, sir.
Omega t minus t2. Happy?
Yes, sir.
इनटू ब्रैकेट. चलो लिखो, ब्रैकेट में क्या होगा? माइनस f by k. Happy?
Yes, sir.
Cos of omega d t minus t2. Happy? Minus f eta omega upon k omega d sin of omega d t minus t2. Do you agree with me?
Yes, sir.
हाँ, एंड ये मल्टीप्लीकेशन के बाहर ये f by k है, प्लस f by k है. Do you agree with me?
Yes, sir.
So this plus f by k and minus f by k, they are going to get cancelled. Agreed?
Yes.
So what is the final response? So response of this single degree of freedom system, this type of loading, I will write down it here and then we are going to plot it. Are you with me?
Yes, sir.
And then we are plotting. We may not plot it in today's class because time is just about to get over. But what we will do is we will have some physical expectation on the response. Do you agree with me?
Yes, sir.
हाँ, तो प्लॉट कल करेंगे, लेकिन कैसे दिखेगा रिस्पॉन्स वो आज करते हैं. आर यू विद मी? वी विल ट्राई टू अंडरस्टैंड हाउ विल इट लुक लाइक. अब जरा देखो यू
Yes, sir.
सो कैन आई टेक, no, I can't take e raised to minus eta omega t common because here it is t minus t2, here it is t minus t1. Are you with me?
Yes, sir.
So I will have to write it separately. E raised to minus eta omega t minus t1. Happy?
Yes, sir.
Into bracket. क्या लिखना है? थोड़ा सा रिवर्क करना पड़ रहा है, but we will do it. So minus f by k cos of, in bracket, omega d t minus t1. Happy?
Yes, sir.
ब्रैकेट कंप्लीट. देन दूसरी टर्म क्या आने वाली है? माइनस एफ ईटा ओमेगा अपॉन के ओमेगा डी. माइनस एफ ईटा ओमेगा अपॉन
Omega dk.
के, हाँ, के इंटू ओमेगा डी इंटू साइन ऑफ ओमेगा
Omega d.
टी माइनस टी वन. राइट?
Yes.
टी माइनस टी वन. वो एफ बाय के तो कैंसिल हो गया. हैप्पी?
Yes, sir.
और ये ऐसे के ऐसे कॉपी करना पड़ेगा. और ये सबट्रैक्ट करना पड़ेगा. किसमें से सबट्रैक्ट, मतलब सबट्रैक्ट करने के लिए क्या चेंज है? T1 will be replaced by T2. Here it will be T2. Are you with me?
Yes, sir.
Here it will be T2. Everything else is same. T2. So this is going to be the response of the single degree of freedom system to this kind of excitation. Now, what do you expect? What should this graph look like? तो जरा ये एक्सपेक्ट करते हैं कि u of t के ऊपर हमारा एक्सपेक्टेशन क्या है. Are you with me?
Yes.
If you are hearing the background noise, those are the kids playing downstairs. So please pardon me for that. So this is time t and this is u of t. Are you with me?
Yes, sir.
How does the response of this system look like? So t1 tak the response 0 hai. Do you agree with me?
Yes.
The response will be 0 till t1. Happy? After that, you have a force F and stiffness of the system is K. So you are going to have a line which is drawn at F by K. Do you agree with me?
Yes, sir.
So if this load would have been applied statically, the system would have come to F by K. Do you agree with me?
Yes, yes.
Deformation. But as it is not applied statically, what you are going to see is this kind of behavior. Do you agree with me?
Yes.
It is going to vibrate about that. Now, how does the response looks like depends upon what is the difference in T1 and T2. If the difference is sufficiently large, then you will see that it is settled down here, somewhere here. Are you with me?
Yes, sir.
It will vibrate with a very less oscillation about F by K. Happy?
Yes, sir.
So first possibility is this. And then what is going to happen at time t equal to t2? वैसे देखा जाए तो t इक्वल टू t2 पे तो रिस्पांस क्या होना चाहिए? 0 होना चाहिए ना. because
Yes.
the load has dropped down to 0. But it will not suddenly, it will not go to 0. It will go something like this on the other side. Again, you will have oscillations about 0 because 0 is the new mean position. Are you with me?
Yes. Yes.
As the load is suddenly dropped, you expect that you will see the oscillations like this. Are you with me? And
Yes, sir.
finally, it will come to the rest. This is T2. And this time is greater than T2. Happy?
Yes.
This is the first kind of response. If the gap between T1 and T2 is narrow, then we are going to see something else. So that's what we are going to do tomorrow. First, we will keep the gap between T1 and T2 sufficiently large. What do we mean by sufficiently large? We will see that tomorrow. If it is sufficiently large, this is the response that you would expect. Happy?
Yes, sir. Right.
Let us see if this function plots to that in the tomorrow's class. So let us stop here today. I'm going to stop recording.